Okay, let's start where we left last time. We are looking for amplifiers, and as I said, this course for the first time, maybe, I don't know, we will concentrate more on MOS technology, MOS device based amplifiers, oscillators, op amps. Though as and when I need and as and when I feed, I will give you something equivalence of bipolar as well. Okay, so not that bipolar is out, I keep saying every time. So today we shall look into typically MOS amplifiers. We have already solved one problem for MOS, but just to give you more details, there can be three possibilities of an amplifier made in MOS with MOS devices. One is NMOS amplifier. So the word here is the transistor which gives you a GM, is called the driver. Is that word correct? The driver transistor is the one where input is received and which gives you GM times something at the output. So for example, take the first figure, this transistor is called driver transistor. So if it is N channel kind, it is called NMOS amplifier. If it is a second part, like it is a P channel device, that is called PMOS amplifier. If there are both P channel N channel gates are connected, this will be called CMOS. We have already done CMOS, or I don't know whether you may be doing now in your digital course. So this is called CMOS amplifiers. And then the first part of course is the driver. What kind of driver you have decides the name, NMOS, PMOS or CMOS. Then there are other names also we give. One is called based on loads. So you have an NMOS amplifier with first one is resistive load. You can see resistance is the load resistance. In the case of fourth, the resistance is replaced by a transistor, okay, that is equivalent of that, and this transistor acts like a resistor, okay. So it is called, and this transistor we shall see little later, this device is always in saturation, and a saturation transistor resistance, we know why it is higher in saturation, because the characteristics are very flat, R0 is roughly its resistance. So typically by changing the size of this transistor, I can change the W by L of this transistor and hence the resistance. So the resistance of the load is varied by changing the size of the load transistors, okay. If instead of N channel device as a load, I can also have a P channel device. This circle stand for, sorry I should have made, this is where I differentiate between N channel and P channel. A circle at the gate is a P channel device, no circle at the gate is an N channel device. So if you have a P channel device and to make N channel device, this was my gate, this was my drain, this was my source. Can you tell me, since MOS transistors are identical from source to drain, most cases, they will be asymmetric in some case, but otherwise source drain can be interchanged. So why did I call this as drain and not as source? Why this upper lead here was not called source? Because they are identical. I can call this drain and this source, but I did not. In N channel device, which carriers make transport? Electrons, is that correct? Since electrons come from source to drain, the actual current will flow from where? Positive terminal to negative. Since the actual current is going down, the electron current is going up, that means source should be lower than the upper side, because otherwise electrons can't move up. Is that clear? That is why they were given such names. So in same logic, can you think what I did here, which will be source here? Upper one, because now holes also travel in the same directions as the normal current, positive polarity down. So this is source, this is drain, and again gate is connected to drain. So whenever gate is connected to drain, whether in N channel or P channel, transistor will enter saturation, and its equivalent resistance can be evaluated by finding the W by L. Write the equation, we will do that, and we know what is the resistance we are offering. So what exactly we did, we replaced this so called RD by equivalent resistance. What is the advantage we get? You have not done any technology, you are not aware, but just for the heck of it, any idea why I am trying to replace resistances by transistors? Less area. Typical values of this resistance will be 40k, okay, 20 to 40k. Now if I substitute, if I put an actual silicon, it will take more than 20 transistor area for one resistor, okay. So to an integral circuit, what is our importance? As many transistors I can pack per unit area, that is the density of the transistor, and that is what I am increasing every year, okay. That is what Moore's law said, pack. So if I put resistor, all that advantage I will lose. So I am trying, particularly integrated circuits, we will normally never use RD, but for our circuit course, as much if I put RD, it does not really matter because it is external. I can go to the breadboard and buy, take some 40k resistors from the rack and put there, okay, we can test it. But in real life, when it goes to chip, we never put any resistances on chip any day unless it is necessary in case of RF circuits. So is that correct? There are two kinds of loads, N channel saturation, P channel. There is third one which I forgot, maybe I can show you here. Which is this load transistor is? There is a line shown here, means already transistor is on without VGS applied and it enhances as VGS increases. Where does it shut off? At minus VT, okay, at minus VT. So this is called depletion loads. So there are three possibilities. Of course you can always say another one which is maybe more generic, let us say only N channel loads, and this I call VGG. If VGG is equal to VDD, then what is the status of this transistor? VGG is equal to VDD, that means I am connecting to power supply, it is a saturation, that is what we did. If VGG is greater than VDD by 1 VT, more than a VT, then what will be status of this? It is in linear mode, it is in linear mode. So what is the resistance in linear mode? Extremely low, it is a linear and R is very low. So in some requirement, if you want lower resistance, what do? We do not put it to VDD but put it to higher voltage and actually use linear circuit, linear device there. Is that correct? So that R can be further reduced. In case, as I say, I am not saying, where do you think R smaller will be required? What R smaller means? Does current increase or decrease? Increase. So if you have, this is what digital people do, if you have a capacitive load here and this is to charge this, what will be if R is larger, what is the time constant? Larger. So switching frequency will be lower. So if R is lower, switching frequencies are higher, so is the bandwidth connected to it. Is that correct? So somewhere power and frequency are getting related. Did you get the point? Larger the current, higher is the switch, okay. Lower the currents, that is low power, lower speeds coming up. Is that correct? So this is somewhere connected to us. So our choice is not, in our normal circuit we hardly care of power because we say breadboard, pankha laga denge, chahe to coolant dal denge uspe. Nothing can be done inside a chip like this. So we have to be extremely worried about what power we actually dissipate per unit area on silicon chip. And if you have seen my some graph, microprocessor these days are consuming so huge a power, it is like a rocket nozzle of a huge launcher, rocket launchers, so many thousand degrees of centigrade there. So one has to understand that why we are worried in power specifically on a chip, is that clear? But not in so much in, like if you have seen a desktop computers, you see it is a big box, a huge fan is sitting backside, cooling it, all PCBs are cooled by huge fans there, it is running at very high speed around 600 RPMs. So what is the advantage there? You have a space and you have a fan, you have a power supply 220 volt, no problems. On a chip 1.2 volt supply or 2 volt, 1.5 volt supply of which battery is inside, and that is that. So you have no way to run a fan there, is that clear? And therefore on the, this fact has to be understood, because when you go ahead you should realize why sometimes we are so catchy about power, because there on that chip we are only worried about power as of now. In our course I may not say so much, but just to make you point why all these differences were shown, because these are the kinds of amplifiers we may use in chip as well as on the breadboard. That is called discretes and integrated circuits. Discretes we may never use this kind. Why do I use this? I have a good resistor, baba, acha hai. So this has to be understood, that why I am showing you both all the time, because in future you will be hardly working on a breadboard, you will actually work on chips, is that correct? So you must know what is the difference when I go on chip designs or chip circuits. There is just now I said different kinds of loads, some of them I showed, some others are also can be shown here. This RD can be replaced by a current source. Since you say RD is higher, a current source, the output resistance is higher or lower? Higher. If it's a current source, the output resistance is very high. So I say if I put a current source here, fixed current source, which I can create from where? A mirror. You can see if I push a current here, reference current, this current I can adjust to any value. Is that clear? This I will show you in a diff amp how do I actually bias, but just take it. Equivalent current source can be transferred to an amplifier as a load by simple current mirrors, okay, simple current mirrors. And another thing which I just now said about the saturated loads, how do I calculate resistance? I connect gate and drain to VDD, write the equation device if it is in saturation, first assume in saturation, let us say it is, because VGS minus VT is less than VDS, VGS equal to VDD means VGS minus VT is always less than VDD. If I use this delta IDS by delta VDS is essentially the 1 upon R of this, which is, if I differentiate this, so R is beta lambda VDD minus VT, is that clear? So by what is beta contains? Beta dash into W by L. So changing the size, I can change the resistance. Lambda is a technology parameter, beta dash mu Cox is a technology parameter, Vt is a device parameter, technology parameter. So all that you can do is change W by L. So different sizes of transistors will give different resistances. Is that okay? Is that okay? So this is how the loads are created in MOS amplifiers. Last people, is it clear? Loads can be created out of transistors themselves, okay. And what is the advantage? I say the area of this will be 1/100th of the area of the same for equivalent value of resistances, okay, and that is what we are really looking for. How to calculate resistance? Just delta I by delta V and inverse of that is your R. So nothing great happens, just write equations, differentiate and get your resistance. Is that okay? Of course these equations which I write you need not write, just want to show you that what is it. You just, I need not have written all that, I would have directly written here, but I thought you should know why, how do I calculate, okay. This is only to show you methods, this formula is not relevant. This is the method which I am showing how to evaluate R's in a transistors, okay. Okay, something you can see, okay, thanks for suggesting. If you leave lambda per se, lambda is 0 for example, this equation is quadratic, it's a parabolic equation, okay. Now if you see a IV characteristics of a diode, how does it look? It's something like this. And if I put a parabolic equation, it is something like this. So it closely replicates the diode characteristics. It's actually opposite, depends on the parabolicity. It may be much higher or much lower than that, but in normal cases it will be almost as if following diode equivalence of that. That is why it was called diode connected. Is that clear? Please remember this is only valid when VGS minus VT is small enough, okay. If it is too high then it will go like this, then it may not actually look like diode characteristics. Is that okay? Why diode connected? Okay. Okay. There are another ways of defining the amplifiers, which is basically circuit based, and these are, an amplifier can be have a common source terminal. What do we mean by common? Between input and output, whichever terminal is common, we say it's a common that. So if source is common between input side and a drain side, output side, then we say common source. The other possibility, it may be a common gate, okay. Common gate is essentially what means? The gate is common between input and output. So where will be input? At the source side, and where will be your output? At the drain side. Gate is common between input and output. And the last is common drain, okay. Now this common drain is very important circuit for every one of us, okay, and it's also called source follower. In BJT what it will be called equivalently? Source in BJT is what? Emitter. So it's called emitter follower. Emitter follower is identical, at least in nature, as common source amplifier or common drain amplifier, which is called source follower. We will do some analysis for common source. Please read the this our Setas Smith book for bipolar circuits equivalently, okay. Okay, so here is a first amplifier which we did partly last time, but repeat again. You have a common source. Please remember, now here is gate, here is drain, and here is a source, okay. Now you have a source which is common to input and common to output. Therefore it is given a name, common source amplifier. Now the only difference between this and the other one is, this source has a source resistance Rs, source has a source resistance Rs, which is shunted by a source capacitance Cs. Is that okay? So at DC, what will happen to this Cs? At DC means frequency 0. Is the impedance lower or higher? Higher, open circuit. So for a DC, as if capacitance does not exist, Cs doesn't exist. Is that okay? 1 upon omega C, if omega is 0, the impedance offered is infinite. This Cs will offer infinite impedance against Rs, means open circuit to Rs. So Rs is the only resistance. So we say a DC capacitances are, this capacitance is open circuited. But there are two more capacitances I have put here. Their values also should be such that at DC values they should act like an open circuit. What does that mean? That the DC voltages here, which I am going to apply, should not get connected to power supply. They should be blocked to power supply. They may modulate other side then. Is that correct? This DC value here should not get directly connected to input source. So what should we do there? Put a capacitance which is called series capacitance, called coupling capacitance. What does it decouple in fact? It should be called actually decoupling capacitance. What it decouples? The AC source from a DC source. Is that clear? AC source from DC source. Similarly from the output, this is VDD. I want to remove this, I do not want to couple this VDD, which is the power supply, DC power supply, to the AC output, which is V0, okay. So is that point clear to you? At this point, what will be the signal? DC plus AC, and I do not want DC to be outputted, I want to only see AC amplifiers, okay. So what should I do? I should block DC. This CC2 is again the same blocking capacitor or a decoupling capacitor between power supply and the AC signal, AC outputs. So what should be their value? Should be 1 upon omega C. I want to be very high. 1 upon omega C for DC, it has to be, it will always be open circuit. But for a lower frequencies or a moderate frequencies, what should you act? Whenever for AC signal it should get in. So what should be the impedance offered by these? Practically 0, practically 0. So what should be the values of them, because omega are not going to be very high, we are going to use smaller frequencies as of now. So C should be very high, so typically some microfarad, 0.47 microfarads or a microfarads could be the decoupling capacitors, or this is that some experiment you may be doing, you can think why we are putting a larger value of C in the series connections. Same way for this, at all the AC frequencies it should act as open circuit. So what should be the value here? Please remember, I repeat, for DC it should be open, but for AC it should actually be like a short circuit to RS. I don't want RS to be part of my AC circuit. So what should be the value of CS? Please think of it, 1 upon omega C, okay. I want at a given frequency of operation, this should act like a short circuit. C should be again high enough, because then only it will act like a, and which capacitors normally you put there, have you seen there? Say electrolyte large value capacitors which we put across this device, is that clear? So this C's purpose is at AC frequencies it will short what? RS, but for DC frequencies it itself will open up and only RS will appear in the DC network, is that correct? This is how an amplifier biasing will be done. Now bias is done as usual, like a fixed bias as shown here, RG1, RG2 to VDD and to the gate, and equivalent resistance is how much for from Thevenin's? Please remember here it is very easy, no gate current, divider is Rg2 upon Rg1 plus Rg2 times VDD, that is your Thevenin's bias what you are want, VGS, and how much is resistance it will offer? The parallel combination, and that value I have kept here as Rg, is that correct? Rg is nothing but Rg1 parallel Rg2, is that correct? So that resistance is not shorted or opened by capacity, it's bias, it must sit here. If Rg doesn't exist, what will not exist? The DC bias for this will not exist, is that correct? DC bias will not exist. This is the most important part in the actual circuit when I draw. So having shown you a common source amplifier, what is my ultimate aim? I will like to find V0 divided by, okay, I think we are making mistakes, so we call it RS dash here, because you know this RS is a source resistance. So we start calling R series or R source, or because R source is sitting here, so that name should not get confused, okay, is that okay? Maybe they call it in the book, I think if I am not wrong, they are calling R signal, okay, R signal generator, okay, R sig is what they are talking about, okay, fine. If I have this circuit, then I can draw equivalent of that. At the input side, you have an input source Vin, you have a series resistance of the signal source Rs dash, you have the Rg larger resistance of bias network Rg, and they have a gate here, is that okay? This is, if you have just seen the circuit, you can see this is the input side, okay. From gate, okay, this is my source, from gate to source there is no connection. As far as AC is concerned, there is no connection between gate to source. Please look at the circuit again, if you, just a minute. Between gate to source there is an insulator, so there is no connection between, which is in contrast to what? Bipolar. If this was your base current, how much current would have been flowing here? Beta plus 1 IB. So there is a much easier case in the MOS, because there is nothing actually comes out from the other side. So ideal device in some sense. Now for this other side, at the output equivalent of that side, you can see what is the output model we have said. Whatever is the VGS signal appearing here at the gate with reference to source which is grounded, GM times VGS is the current source, GM times VGS is the current source, shunted by what? R0, which is the output resistance of the transistor, okay, output resistance of the transistor. So this is actually equivalent transistor source GMVGS parallel R0. What is this RD? RD is the drain resistance which we have put there. And what is this additional RL I am showing you here? This is external load which I do not know, this may be coming from external side. So that is my actual load which may be RL, okay. So if I show you now, it is R0 parallel RD parallel RL. Now we also need to find, apart from gains, two more parameters. What is the problem I said in connecting the two circuits in bipolar? The output impedance and the input impedance are sometimes equal or bad, okay, one is much lower than the other, so it is called loading effect. Now I want to see how much is the R in and how much is the R out of my circuit, so that can I cascade. What do you mean by cascade? The output of the first stage is given to the input of the next stage, is that correct? This is called cascade. So can I cascade? Another word which I am going to do after this is cascode. What could it be different from? What is the word I used earlier also I once said? Cascode amplifiers have one advantage. What is the disadvantage it gives over the normal amplifiers? I said you something. We have not talked bandwidth, so you will not remember it immediately. We said gain bandwidth product of an amplifier is constant, okay. This is called figure of merit. If you increase gain, bandwidth goes up, we will see the expression later. Cascode, what it does? It breaks this limit, okay. That is exactly what it is doing. The gain can be enhanced without losing bandwidth, and that is exactly what all these years we were looking for. Okay, I do not want to lose my gain at the cost of increasing the bandwidth or retaining bandwidth at higher gains, okay. This is exactly what cascode does, okay. So we will go to cascode amplifier later, but let us right now think that this word should not be confused any day, okay. So what is VGS value? If you look at this is I hope that you have done basic circuit course reasonably good. This is simple mesh equation. This voltage equal to this plus this into Vin, it is a potential divider, so it is Rg upon Rg plus Rs dash time Vin is your VGS, and which is the case when it is equal to Vin? When Rg is much larger than Rs dash, you can say okay, all that input signal is available as VGS, but this condition must be met, is that correct? This condition must be met. If not, you should use whatever value Rg Rs dash has, you use there. It is something like saying, since there will be something in denominator larger than numerator, it will be less than VGS, will be less than Vin, but it may be 0.9999 Vin, so why should I worry about 0.59, I say Vin, okay. So the idea is to know where to when use. These are all things which I am trying to show you in real circuits. What do I assume? In this course, since you are doing analysis, please write everything, okay. I am not giving you values. So in analysis you should show what it is, but in real life I do not use that. I say okay, this is past, okay. This has to be understood why we quickly do things much earlier than others, not because we cannot solve this, we just know how, anyway that is same kind of thing, okay. Okay, at the output side, what is the current? Only current source is GMVGS, but the direction of current is what? From drain towards source, is that correct? GMVGS, but the output is always shown as plus minus. So what should be the sign? Should be given opposite, because GMVGS will actually go from like this, but voltages are measured like this. So we say V0 is minus. This minus is very important. What does it mean in circuits? Minus means invert or a phase of 180 degree, phase of 180 degree. So if your input signal is in one phase, the output is always 180 degree out of phase from the input. This is the most important characteristics of a transistor, that the output is 180 degree out of phase from the input, which is always 180 degree, okay. but if you manipulate some external circuit, this 180 plus or minus you can do additionally, and that is exactly what we do in our real life, to change this 180 plus minus something to get the phase I want, but transistor per se will always give you 180 degree. It cannot change it to 179 or 185. This is fixed 180 degree minus sign. Minus is coming from where? J square. Is that correct? J is 90, J square is 180. Is that correct? This J vector, J is 90. So J square is 180 degree. J into J. Okay. Is that clear? This is coming from very simple circuit theory. Okay. So this is R0. All these resistances look to be in parallel. R0, RD, RL, everyone is in same across this. So Gm times R0, RD, RL into Vn is the output, V0 by Vn is the voltage gain, which is minus Gm times R0 parallel RD plus RL. However, this was under an assumption that VGS is Vn, is that correct? It was an under assumption that VGS is Vn. Otherwise what would have come here? VGS, and then what should I replace with? RG, multiply RG upon RG plus RS to make it same value as the gain. Is that correct? If I would have said this is not Vn but then VGS, then I would have replaced this VGS by RG upon RG plus RS times Vn, and then another factor I would have multiplied here is RG upon RG plus RS dash if Vn is not VGS. Is that okay? This is as simple as that. Okay. So now you got the gate MOS gain. So what it depends on? R0 is not in your hand. To some extent it's in your hand. What is it? How R0 gets controlled by? No, lambda is fixed. Lambda is somewhere fixed. Okay. So ID 1 upon lambda IDS is R0. So the IDS is coming from where? The bias network. IDS DC bias current is decided by the bias network VGS minus VT. Now that value is giving you capital IDS, is that correct? DC value, and that may decide what? The GM. 2 beta IDS is GM. So GM actually decides how it is? Under root. Please remember GM is proportional to root of IDS. R0 is inversely proportional to IDS. So by adjusting IDS, I can say some way GM times R0 can be modified. However, RD, RL are externals. Okay. So normally what will happen? RD and RL will be smaller, much smaller compared to R0. How much will be R0 typically? Mega ohms. How much will be RD, RL? Few hundred tens of kilo ohms. In normal case, RD parallel RL will be smaller than R0, so you can even neglect R0. Is that correct? Neglect R0, but otherwise as a theory you can retain it. So by changing the bias current, what does bias current means? In essentially biasing point, your operating points, if you vary, your gains will also correspondingly vary. Is that okay? That is what exactly we were trying to show. Okay. Is that okay? Everyone has seen? Okay. There are two more parameters of interest, as I say, for input impedance and an output impedance. Okay. Before we show it, I will give detail how to calculate for any network. I think you must have done it. If you are given a network, you can always find the output impedance and an input impedance. How do I calculate these impedances? Short the outputs, okay, and from the input side apply an input source with the input resistance Rs of, you can even make 0. Whatever current and comes out of this Vx by Rx is input impedance. By same logic, short circuit all voltage sources at the input side, is that clear? Open all current sources, independent current source. Please remember this is independent actual sources. Short the voltage source, open the current source, apply Vx at the output, find the current entering from that node, Vx by Ix is R0. So the method is identical to the circuit theory which we have done. Sometimes by observation we will use it, otherwise you can always do this for any larger circuit. Is that correct? This time this is so obvious, so I did not do analysis, so I just want to show you that this is what I am going to do. Normally RL is not considered to be part of output resistance. Why? It is external, I do not know what people will give me, okay. So normally R0 is taken across RD. Even some people believe actually you should measure intrinsic R0 also, that is without even the drain resistance. Is that correct? So it will be always R0 in most cases, okay. So okay, if I do that, then one can see from the circuit, there is no actual, as seen from here, this is the only resistance it is seeing. So whatever current entering V by I is only Rg, whatever is voltage here divided by Rg is the current, so this divided by that current is same as Rg. So input resistance is Rg, input resistance is Rg, very high. How much it will be? In mega ohms, because Rg1 and Rg2 also are in mega ohms. So because of them we will always have Rg very high. Is that correct? Rg very high. So input resistance of a MOS amplifier is normally decided by the bias network and typically is the order of few mega ohms. Is that correct? Typically. Why I am saying typically? Because values you choose Rg1, Rg2, I do not know. If they smaller, then it will be smaller as well. Okay. What will be the output resistance seen again from here? By same logic, short here, then the VGS is only coming from here. So what is the resistance will be offered here? You open this, RD parallel R0, forget about RL. If you see a resistance coming from the outside and if I put a voltage source and find current, V by parallel, this is the current, this I am opening, okay, this I am opening. So if I put a V0 and two paths, that means parallel, so V0 by I is the parallel combination of R0 parallel RD. So the output resistance is R0 parallel RD. Typically R0 is of the order of mega ohms, RD is of the order of few kilo ohms, tens of 20 kilo ohms. So what is the actual output resistance can be talked as RD. So output resistance of a MOS amplifier in a common source technique is just the drain resistance which I apply, and that drain resistance decide what? Apart from it also, please remember, drain resistance also decides the operating point. Is that correct? VDD by RD, this is giving the maximum current. The load line is decided by the RD, and the RD is essentially the output resistance. If you want accuracy, you say RD parallel R0. Yes. So what is that clear? Since I did not do actual calculations, I probably messed up, but otherwise you can think that by observation that is correct. Okay. So if Rg is not Rs dash, I repeat, Rg upon Rg is, this is the gain of a MOS common source amplifier. Is that okay? This is most important in the case of, is this amplifier will be have a larger gain or a smaller gain? Okay, the three amplifiers I told you, which are the three I said? Common source, common drain and common gate. What do you believe, which will have highest voltage gains? Gate is common to source and drain. Whatever is source will pass to drain. That is what source drain current is same, na? So it is a unity roughly, okay. It depends on the load values at the input and output. I is same both sides, is that correct? So it will be dependent on the values of RD and Rs you are actually used. Whereas there is no GM factor there is no booster there. In the case of source follower, what does that follower means? What follows what? If it is a source follower, what does that mean? The output voltage follows input voltage as it is. That means gain is unity. So common source amplifiers is the only amplifier which will give you reasonable amount of voltage gains. Okay, is that point clear? So they have to understand, but then why the other two are so much talked about? They must have something additional with them at the cost of what? Gains. Okay, I do not have gain, but I must be giving you something better which may still require you to use. Otherwise, I will not study common gate and common drain. Why should I, if they have no gains, no additional advantage, so why should I use that? So there we will like to see, if I change over from common to other, do I achieve something else at the cost of something else? Is that clear to you? This is what we are looking for other two amplifiers. There is another common source amplifier which is very popular. Okay, another, before we quit here, this equation you can see here, R0 is equal to how much? 1 upon lambda ID. Is that correct? Lambda is what parameter we call? Technology. This is decided by the technology. GM under root 2 beta dash. What is beta dash? Mu Cox. Again technology. W by L for external circuit like us have no control, so even that is fixed by someone else. All that I can vary is IDS. Is that correct? So if there is a change in this so called technology parameters because of what? Environment. Let us say basically temperature, even humidity changes, but at least basically temperature. If those values change, what will happen to this gain? They will also change with the, particularly with the temperature. Is that correct? So if you have a design an amplifier in a system which should have a gain of say 100 or gain of 40, it may either go down, depend on the temperature which side it goes, or may go up, either way, and then the next circuit will see different input voltage than what you actually plan to, okay, and they also will get corresponding changes. So at the end of the day, cascading circuit may not show the actual gain, it may be either much smaller or much higher, in which it may saturate and it may not even amplify at that. Is that correct? So I am clearly worried that the gain function should not be a very strong function of technology. If that happens, then I say I am safe, because then I know what gain I am using. Is that correct? But let us see whether the next circuit does that, and at what cost. Okay. Now if you see what is the difference between the last circuit and this circuit? No, everything else is same, except the source resistance is not bypassed by CS. Is that clear? Source resistance is now available to you both in DC as well as in AC. Is that correct? Is it okay? Source resistance is not bypassed by any capacitance. So this is called source amplifier with source degeneration. Okay. Now can you see RS for an AC equivalent circuit? We will draw it. This will be now part of the input as well as part of the output. Earlier IRS was getting bypassed, so no worries. Now you have a problem that RS is common to both sides. Okay. And let us say if I draw an equivalent circuit of this, where does this RS appear, and why should it then say the gain will be independent, roughly independent of technology parameters? Is that clear why I am worried about technology parameters? Because the temperature is a strong, which will increase, do what you, okay. Even if you put a fan, why fans cannot cool very quickly, all that? Which law does not allow that to happen? Newton's law of cooling is proportional to the difference of temperature. Nothing much, I can accelerate it by removing the heat around, but the actual cooling will go by law of cooling. Is that correct? Proportional to the difference you are looking for. Is that clear? Do you know, do you still recollect your law, Newton's law of cooling? That the rate of cooling is proportional to the difference of the temperatures. Okay. So initially it cools faster and then it starts cooling. As you come closer to room temperature, 28 degree to 23 degree, you may take 2 hours, okay, because the difference is very small now. Okay. So the worries with us is that ambient temperature you may remove, but the actual cooling will be slow. Is that correct? Now that means there will be a variation of gains irrespective whether you like, you do not like. But I will like, I won't like that. So I should do something which this circuit probably does. The circuit analysis is almost identical. The only difference Do you see something difference in equivalent I had drawn now? This RS I had drawn from source to the ground. But remember this RD and RL are not going to source now. Is that clear? Where are they going in the actual circuit? RD going to the ground, RL going to the ground, but not going to the source because source is not grounded. Source has an RS going to the ground. So equivalent, have you seen this? Please look at this circuit. This RD is grounded, this RL is grounded, this is of course your V0, and this is your source which is not grounded. What is it? So I should not connect RD parallel R0 parallel RL now. Is that point clear? The difference what is going to get is this, that RD RL are parallel but not parallel to R0. Is that correct? Because they are two grounded. R0 is only going to source because that's how I define R0. For the sake of it, maybe we can say lambda is very small. First case we may say RG is much larger than RS, sorry, this is called RS dash, and we say R0, first simplicity. So this is your V in with reference to the ground. Okay. Please remember this V in or this value is not same as VGS. Please look at the circuit again. This V in, because this is grounded but this is not grounded, is that correct? Is that clear? V in is grounded but this terminal is not going to the source, it is not going to ground but to the source. So I now write a Kirchhoff law. Okay. I start from here V in and I calculate the voltages how it falls. So first is V in is equal to VGS, this is V in, so VGS plus what is the current flowing in GM RS? GM times VGS is the current flowing in the RS, is that okay? This is VGS plus this drop I want to know. What is the V into the ground? This voltage plus this voltage. VGS plus IRS, whatever flowing through this. This is my V in, is that okay? How much is VGS? I will find out. So this is VGS plus GM times VGS into RS is equal to V in. Is that okay? I repeat, this voltage plus this voltage is the ground to this voltage. Is that okay? Divider, this plus this is this. Okay. So GM VGS into RS plus VGS, which is equal to VGS times 1 plus GM RS. So how much is VGS now? VGS is V in upon 1 plus GM RS is your VGS. Is that okay? Just solve this equation. So VGS is equal to V in upon 1 plus GM RS. Is that correct? If RS is 0, what is the condition we will get? V in is VGS, that's what we did if RS is 0. Now I say RS present, so all that it has reduced something. This is called degeneration. The word is degeneration. Input is degenerated now by 1 plus GMRS term, okay, compared to earlier. Okay. But what is the advantage of doing all this? Okay, you must be getting something out of it. Okay. If this is open circuited, same current passes through RS, so GM VGS into RS is the drop across RS plus VGS must be equal to V in, solve it and you get this expression. Okay. Simple circuit analysis. How much is V0 from here, from our circuit analysis? This current is actually putting GM VGS is the only current source which is also passing through RD/RL if R0 is infinite. Again the idea is R0 is infinite. So I write GM VGS RD parallel RS is V0, then I replace V0 by how much? V in upon 1 plus GMRS. So I get AV is equal to V0 by Vn minus Gm upon 1 plus GMRS times RD parallel RL. Okay. I repeat, if GMRS is much larger than 1. What is GMRS is larger? It may be. GM is typically of the order of how much? 10 to power minus 3 or kind. RS may be 10 kilo ohms. So it will be around 10. Okay. So we may say if GMRS is larger than 1, GM upon 1 plus GMRS is 1, and then you get then GMRS GM cancels, then I get RD parallel divided by RS. Can you now see the voltage gain does not have a term which is technology related? Is that okay? The voltage gain of a common source amplifier with source not bypassed or degenerated source, then we get a gain which is ratio of load to the source resistance. Is that correct? None of these two terms are anyway technology dependent. What is the criteria only to do this? GMRS should be larger than 1 or RS should be larger than 1 upon GM. That's what exactly. How to make a RS value? So RS should be greater than 1 upon GM. GM is decided by the currents you are already passing in the DC currents. So you find out the choice of, so now it said you must understand there is a problem. In calculating a bias network you need an RS value, and to get RS greater than GM also you have another inequality going on there. Solve together such that both conditions are simultaneously satisfied. Is that clear what I said? In calculation of a bias point, operating point, RS is appearing there also. But the condition I am now saying, and GM is you are using, so condition I am saying use GM, 1 upon GM should be smaller than RS. Okay. So you make some choice of RS first, get that bias point using this and recheck whether that satisfies your proper saturation active mode conditions, and then also see that this value is equally satisfied. Is that correct? If that does not happen, then you may have a problem of instabilities. This does not happen, normally we know how much to keep, so that value 10 times is good enough for all cases. Okay. So what is the advantage of this again? RDs will be order of, RDRL will be order of few tens of kilo ohms. RS will be of the same order. So what will be typical gains will be 2, 3, 4, 5. Typically the gains will be 2, 3, 4, 5, even 1 if they are equal. Okay. So what does that mean? We have achieved something at what cost? At the cost of voltage gain. I say okay, I am stabilizing it. Okay, I am getting now an amplifier which is temperature independent. Okay. Why it is temperature independent? Because even these are temperature dependent term. R has a positive temperature coefficient. But since they are on the same, assuming same material carbon resistor, the temperature coefficient of R and numerator denominator may almost be similar, and therefore they are independent of temperatures. Is that correct? Is that clear? So what is the advantage I got? If I want a very stable gain but not very large gains, then I should use common source with degenerated source resistance. This is how. So at very large cost I paid, I would have got a gain of 100 and now I am getting 5. Okay. But I am now saying कुछ भी होने दो, gain तो यही है. That's exactly what circuit people want. Okay. They want to know, is it stable? Is it fixed? Okay. Is that okay? So something, so wherever the first stage of amplifier or wherever you feel that it is more prone to ambience, there you first use a low gain amplifier, which is common source degenerated source amplifier. Then ahead you may use normal amplifier for next boost, which probably is away from it, so that it is not that much temperature dependent. Is that clear? So this particularly happens in instrumentation or measurement systems. The sensor part is in an environment which may be bad. Okay. So there when I boost the signal, I must have a constant gain signal. Is that correct? Once I come out of that, then I can amplify because I have come out of the system now. Is that clear? So whenever there is an instrumentation sensor measurements, the first stage should be this kind because it should give you almost stable outputs. Is that correct? And then as you get the signal, you have a 1 microvolt signal and you say now you have a 5 microvolt fixed signal, the next stage may be a normal common source amplifier. Is that okay? So I am not really worried about large boost, but I want to get out of this temperature variation and have a good signal for me. Okay, this is what essentially we do. So two amplifiers we saw, one is common source, the other is common source with source degeneration. Here is some quick problems, I will not solve it fully, I just want to show you how to do it. Typically you are given a value of, this is taken from Sedar Smith's book, so you can see the values. RG1, RG2 have been given like this, VDD is 5 volt. Okay, in analog circuit, in my first slide I show, it's a dual rail supply. What does that mean? I said, you may have a power supply at the top, VDD side plus, and at the source side minus, but the actual voltage will be VDD minus VSS, and since it's minus, actually it sums. So if a 5 volt supply I want to use total, so what should be VDD VSS if they are to be equal? 2.5 plus minus 2.5 down. Is that it has some advantage? Maybe in the quiz I will ask you read today. Why I should have 5 to 0 is not as preferred at 2.5 to minus 2.5. There must be some advantage, difference is still 5. So why I want 2.5 minus 2.5? There must be something more to it, look at it. Okay, right now the values chosen in from Sedra Smith are these. RD parallel RL is given to you 7K, source degenerated resistance is half K, source resistance, signal source resistance is 0, beta n is 2 millivolt per lambda is taken 0, threshold is 0.8, okay. What does this beta n means? It includes W by L, it includes W by L, beta n dash W by L, together I have given you a value of 2 milliamp per volt square. So what is the Rg value in our equivalent circuit? Rg1 parallel Rg2, so whatever parallel combination from there. The DC analysis if I do, which I did, VGSQ is given 1.5 volt, VDSQ is 6.2 volt. This is I have calculated, you can, I am directly giving you DC points. VGSQ is 1.5, VDSQ is 6.25, ID current flowing is given to us, how much? Somewhere given to us, 0.5, okay, if not given assume it now, okay, 0.5 milliamp. Then GM is equal to 2 beta n IDSQ, which is that okay? If these values are given for given Rg1, IDSQ I am given as 0.5 milliamps, then GM can be calculated as 1.4 milliamp per volt, is that correct? Please remember, you must write correct units in circuits. Please do not say marks have been deducted for only units. Oh, it's correct sir, sir to hai but correct nahi hai. I may exist but marks may not, okay. So please remember every place your units must be correct, okay. Okay, R0 is given lambda 0 to infinite. So what is the gain for this amplifier? Gm upon 1 plus GMRS, RD parallel RL, substitute all values, the gain is 5.76. How much gain I told you? It will be around 4.5, 2, 3, 4, 5. So how much gain I got? 5.76 or around 6 you can say. If you use 1 plus GMRS is GMRS, then RD by RS. So look at the value now. Since GMRS is not very large compared to the other ones, very large compared to one, without, if I use this expression then I get gain of 14, whereas if I use exactly, what is the, why I am saying you this? Essentially means this identity is not correct in the value given to you here. Is that clear? If GMRS is not much larger than 1, you may land in such situation, you may get much larger gains which actually does not exist, okay. So in calculations do not a priori believe that GMRS is larger than 1 and remove it, okay. So I intentionally chose this value from the book such that I will show you that I keep saying it's RD by RS, RD by RS, but don't believe me every time because the values given will decide whether, but if you don't do this and only do this, it will take automatically correct values irrespective whether it is lower or smaller or whatever it is. Is that correct? So this example was just to make a warning signal to you that do not go by just my statements because unless you verify this. Okay, since we are, as I say, थोड़ा pedagogy होना ही चाहिए. Equivalent common emitter source amplifier, common emitter amplifier. Okay, all this the amplifier shown last time also. What is the what things are left in all equivalent circuits? Capacitances. Why I left it? I say I am working at low frequencies and all of them are open or short as per as the requirements. Okay, I am not considering them. But where will I consider them? The high bandwidths. I say up to where this will work. At that time I will use full this, and that is our next frequency response of an amplifier is our next topic. So I am avoiding that just here to show that because that anyway is going to come. Here also CC1, CC2, CE are so chosen that it acts like a short circuit for AC, short circuit for AC, short circuit for AC, otherwise for DC they are all open circuited. I repeat, CC1, CC2 and CE are so chosen that they act like a short circuit for AC signals and open circuits for DC signals. Do you see this is identical to MOS? There is, if you replace this transistor by a MOS transistor, how does it differ? There is some difference is happening. What is the difference happening? This terminal there was how much? Gate to source open. Is that correct? Now there is a R pi. Is that clear to you? The first thing you are now seeing that base is getting connected to emitter through R pi, which in the case of gate, is that clear? This is the major difference you are getting from bipolar to MOS to bipolar. Now you can see, sorry, I forgot this, I still draw RE for AC. So what did I do? I actually put a short across to show RE is shorted. The C will bypass DC at the time, but AC it will short the RE itself. Okay. Is the circuit clear? This is R pi, this is GM VBE, drop across R pi, this is R0, this is your RC, this is your external load as was shown earlier. Okay. What is this RBB shown here? What is this resistance RBB? The bias network RB1 parallel RB2. Okay, RBB is RB1 parallel RB2. Same fixed bias we are done. Okay. बायस नेटवर्क RB1 ये जो है ना ये इसका पैरेलल नेटवर्क है RBB. Since in this case RE is bypassed, this is essentially grounded. Okay. So one can say this whole is one connection everywhere. Okay. Which one? Oh sorry, I am very sorry. Huh? Oh yeah, I told you no, actually it is VB also. I told you that actual there is a RE small resistance, isn't it? Emitter resistance is obvious. So emitter is not exactly the lead output. There is a small RE resistance there, parasitic. So we gave a name emitter dash inside to separate it from actual emitter lead outside. I repeat what I said. This was a emitter dash and this was actually emitter lead outside. Since this terminal was given earlier books by Shockley, the person who actually gave equivalent, he called it emitter dash. So base to emitter dash is VB dash. It can be called V pi, it can be called VI, okay, it can be called anything. this voltage across this is called VB dash, because this terminal was given a name E dash, emitter dash. Why? Because there is a RE small capital RS, or what is RES I said, small to the small resistance associated with the emitter region itself in actual. Right now if not given, all parasitics are 0, RC is 0, this is 0, RS is 0, is that okay? If given then you use that. So this is ground now, because emitter is bypassed now. C will bypass the for AC. So this is ground right now, is that okay? This point is ground now, okay. I already said that at low frequency this is 0, this is 0, this is infinite. Please remember SCJE plus C, this should be infinite. I want to open that across any capacitance, the impedance should be very high, okay. Series they should be short, and in parallel they should be open, is that okay? So these are the conditions. If I use the solutions now, Rin is V in by II, which is, you can see from equivalent circuit, Rin is taken this resistance and this resistance in series, R pi RB parallel Ri, RB is RB1 parallel this. How much is Ri? Can you see from here? Between this, how much is the resistance seen? R pi, R pi. So actual Ri is only R pi, is that correct? But that will be parallel by RBB. So the actual resistance is RB parallel R pi, and if RB is larger, then what will be? RB parallel R pi. If RB is larger than R pi, then it's only R pi, is that correct? So actual value you may see in your calculation whether it is coming close to R pi, but in problem solving don't make any conclusions, just parallel and see what value you get, is that correct? Okay, so how much is the voltage across the R pi? This value VB dash is Rin upon Rin plus, now RS is okay because there is no source there. So this is signal source resistance, so Rin upon, please take it, this value, please remember if this is Rin upon Rin plus RS time Vin is your VB dash, is that okay? This voltage is this plus this into Vin as simple divider, okay. So that is the expression I used. So typically it can be written as Rin upon Rin RS Vin, or Vin RB parallel R pi RS RB parallel R pi, write everything, and if it is less then R pi upon R pi plus Vin if RB is also larger. So what is the purpose of doing this? Why I want to know this VB dash? Why I want this voltage? Because at the output the current source is GM times that value, so I want to know what is the value which I am receiving there, okay, is that okay? Is that okay? So I calculate VB dash as just now I said, and now, so what is VB dash? It is just the divider between R pi and the source resistance, okay. ये मैं हर बार ऐसे अलग अलग expression, I am giving you the real values, quick check how much is, so you can see from how much is the actual value you are getting, okay. This we keep giving you all hints is because when you solve many times long expressions, you forget some term somewhere here there, and then your value becomes very odd. So you should be able to know whether this values which you are getting is reasonable, because it should be close to that value. Accuracy may be a little more, 1.001 is close to 1. So if are you getting close to 1 or you get 5, then why are you doing all that? There is some bigger mistake you did, is that correct? So yet these numbers which I am showing you is for this purpose, roughly you should know where you are, okay. Okay, last part we finish now. So now the G output side, you have a current source, of course this is also grounded because emitter is grounded. GM VB dash is the current source, R0, RC, RL are the three resistances in parallel, output is V0, I0 is the current here entering like this. Since I0 is entering like this for the parallel combination, sorry, not here, it should be shown here. So I0 is minus GMVB dash. So what is V0? What is V0? I0 times parallel combination of the 3 resistance. Is that okay? Is that 3 resistance IR is the output, okay, I0 R0 parallel RC. However, I0 is minus GMVB dash is minus GM R0 parallel RC parallel VB dash. So one gain at the VB dash itself you can say call AV0 dash, V0 upon VB dash is minus GM R0 RC parallel RL, but I am interested in what gain? Not with VB dash, what gain I am interested in? V0 by Vn. So I write AV is equal to V0 by Vn, just multiply by R pi upon R pi plus RS Vn is VB dash. So V0 by Vn, GM R pi upon R pi plus RS, R0 parallel RC parallel. What is GM R pi in bipolars? Beta. Let us call this whole resistance parallel combination is RL dash. Then this gain is minus beta RL dash upon R pi plus RS, or more specific RI plus RS. Okay. Is this gain technology dependent? Yes, beta is a temperature dependent term, okay, beta is. So if I do not bypass RE, what will be gain now? As we did last, assuming that resistance takes care of 1 plus GM is higher than GM1, then what will be the value you will get? The load resistance divided by the source the emitter resistance, is that correct? Let us say R0 is very high, which will be, so RC parallel RL divided by RE will be the gain in case emitter resistance is not bypassed, and again it will be independent of temperature or external environment, is that correct? That will be called what? Degenerated emitter resistor, okay, no bypass, but the gain will fall from how much? Huge number, hundreds to 5, 6, 8, 10 kind of thing. Here beta is how much? 100 plus. If the ratio is higher or even equal, the gain is, please remember, even if load is equal to Ri plus Rs, beta being 100, the gain you are getting is 100. If I use unbypassed, I get 100, but if I put unbypassed emitter resistor, it may be just RCRL divided parallel divided by RE, that is it, okay, but it is independent of beta, is that okay? This is common emitter amplifier with emitter degenerated emitters, okay, earlier get a degenerated source, okay. What is degenerate word? Reduce, okay, you reduced it, okay, the effect was correspondingly reduced on the gain, okay, and therefore you degenerated, by advantage you got it. See then, okay, the final value, I am sorry, R0 is R out. You see from here, please remember external resistances are not taken care in calculation of output resistance. Why? Because RL I do not know really, okay. R0 parallel RCs are the only two resistances I have, which is the output resistance, is that clear? Is that okay? So 3 parameters you must tell me every time you do amplifier analysis. Which are the 3? The voltage gain, the input resistance and the output. All 3 parameters must be evaluated before we say amplifier design is or analysis is over, okay. Is that okay now? So today we will stop here, next time we will continue with it little more on MOS, other 2 MOSes